In this video, we're going to look at refraction and total internal reflection in sort of real time and how that actually happens. I'll just explain the setup here. This is an optics kit from the school that you would have worked with if you'd taken the course at school. So here, this is just a power supply that allows us to connect a light bulb to a regular outlet. And I've got it running at just below 9 volts there so that I don't blow the light bulb out. So then we have a light bulb, and then here is a lens to help focus the light. And here we have basically like a little slit that allows only a small beam of light to pass through so that we can take a look at really how the light's traveling. So you can see it allows a thin beam of light to come through. This is just a piece of protractor paper. So you'll see I've got it currently lined up at the 0 degrees along this dashed line, which represents the normal line. And then there's a solid line, which is where I'm going to line up the change of my surface from air to this piece of glass. So I'm going to make sure that it's lined up right in the center. And we'll see how when I have an index or an angle of incidence of 0 going straight through, I get it out also at the 0 right on the normal line on the other side. I'm gonna set my phone up so that it's nice and steady. Hopefully you can see it okay. So first of all, we have our light source coming from air, so from a less optically dense medium, then it's going to travel into the piece of glass, which this sort of flat surface here where the boundary is from the air to the glass is where the change is going to occur in terms of the bending of the light. So as I increase the angle of incidence, so I'm going to turn the paper to increase the angle of incidence, we'll see what happens to the angle of refraction on this side. So remember, our angle of incidence is always measured from normal out, and refraction is the same from normal out. So I'm going to start to increase. I'm going to bring it over to here if I look at it at 30. So if I set the beam up at 30 degrees on this side, it's hitting the vertex, and it's coming out at about 20 on the refraction side. If I keep going all the way to, let's say, 50, so you can see actually here I've got a little bit of light being reflected off the surface, but most of it is still passing through. And with an angle of incidence of 50 in the air, when it moves into the glass, we're getting it out at about 32. So you'll see how the angle is bending inwards compared to this outward angle. And that's because the light slows down when it hits the surface of the glass. Now, it doesn't change again on the way out because of the glass being curved there. If it was a block that was a square, then you would see a bend on the way in and on the way out. So let's keep going. Go all the way up to 70 degrees as an angle of incidence. We're coming out with about 41 degrees as an angle of refraction. So that's looking at the relationship between going from a less dense to a more dense. We're seeing that light bending inwards compared to where it starts with. If we set it up again at the beginning, but this time we start in a more optically dense medium, so if I flip it over, again, I'm going to line it up. So now where the change is going to occur is at the boundary from the glass to the air on this straight line going in that direction. So if I have an angle of incidence of 0, I have an angle of refraction of 0 when I'm at that 90 degree, or 0 really, angle on the normal line. So I'm going to increase the angle of incidence and we'll see what happens. So I'm just going to slowly turn the page and just watch if you can see kind of what's going on. So if I stop here, that's an angle of incidence of 30 degrees. And my angle of refraction, remember we're measuring from the ray all the way to normal, is going to be 52. So this time the angle is getting bigger because the light is speeding up. When it hits the air, it can go faster, and it's going to bend away from the normal line. So if I keep going, now before I do that though, you'll see you have a little bit of light being reflected back inside, okay, but most of the light is still coming out on the other side and being transmitted. But as we continue to look through, we're going to reach a point where okay, here at 41 degrees, where the light's coming in and it kind of like almost disappears on this side. We can see a little bit of a faint line right at that 90-degree mark. This moment is called the critical angle. So it's right when your angle of refraction is at exactly 90. And now I'm gonna go back a second and I want you to watch the reflected light over here. So when I continue, if I go past that critical angle, you'll notice there's a moment right about there where this reflected light beam gets much stronger. So there's some light and then all of the light. Some and then all. And you'll see that as I continue to go and move out, okay, my angle of reflection and incidence are equal. So it's following the laws of reflection, but all of the light is being reflected back within the medium. None of it is being transmitted onto that other side. And this is the phenomenon known as total internal reflection. So all of the light is being reflected back within the medium rather than being transmitted, reflected all back within.